Materials scientists at Duke University have devised a simplified method for calculating the attractive forces that cause nanoparticles to self-assemble into larger structures. With this new model, accompanied by a graphical user interface that demonstrates its power, researchers will be able to make previously impossible predictions about how nanoparticles with a wide variety of shapes will interact with one another. The results appear online on November 12 in the journal Nanoscale Horizons. Faceted nanoparticles can lead to novel assembly behaviors, which haven't been explored in the past, said Brian Hyun-jong Lee, a mechanical engineering and materials science graduate student at Duke and first author of the paper. We have now demonstrated an approach that speeds those calculations up by millions of times while only losing a small amount of accuracy. The forces at work between nanoparticles are called van der Waals forces. These forces arise because of small, temporary shifts in the density of electrons orbiting atoms according to the complex laws of quantum physics. While these forces are weaker than other intermolecular interactions such as Coulombic forces and hydrogen bonds, they are ubiquitous and act between each and every atom, often dominating the net interaction between particles. To properly account for such forces between particles, one must calculate the van der Waals force that every atom in the particle exerts on every atom in a nearby particle. Even if both of the particles in question were minuscule cubes of sizes smaller than 10 nanometers, the number of calculations summing all such interatomic interactions would be in the tens of millions. It's easy to see why trying to do this over and over for thousands of particles located at different positions and in different orientations in a others try to fill space with infinitesimally thin circular rings. The model then assumes that rods whose projections fall outside the projected boundary of the other particle contribute negligibly to the overall interaction energy. The energies contributed by the remaining rods are further assumed to equal the energies of rods of uniform lengths located the same normal distance as the actual rods, but with zero lateral offset. The final trick is to approximate the distance dependence of the rod particle energy using power law functions that have closed-form solutions when distances vary linearly with the lateral position of the actual rods, as is case with the flat interacting surfaces of faceted particles. And while it may sound like they would introduce a large amount of error, the researchers found that the results were only 8% off on average from the actual. While the researchers primarily worked with cubes, they also showed that the approach works with triangular prisms, square rods and square pyramids. Depending on the shape and material of the nanoparticles, the modeling approach could impact a wide range of fields. For example, silver or gold nanocubes with edges close to one another can harness and focus light into tiny, hotspots, creating an opportunity for better sensors or catalyzing chemical reactions. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.